Hi, we are going to discuss today about electric current and current density. Uh, so basically in this video we will discuss what do we mean by electric current and what do we mean by current density. It also means that when an electric current is flowing through a conductor, then how do we define electric current mathematically, and how do we define current density mathematically. So I'll be using some diagrams and some formula, and from that we will be able to learn that what is the quantity current density and what is the quantity electric current. So basically, suppose we have a conductor, and suppose the conductor is in the cylindrical shape, and suppose the current is moving through the conductor. So basically it is said that when electrical charges are in motion, the current is usually opposite to it. So basically, if there is a delta q amount of charge, and if it is crossing an area in current in the time t, in the time period t, then we can define electric current as I is equals to delta q upon delta t. So here the arrow above the lowercase I indicates that current is a vector quantity. I mean, it's necessary to also know the direction of the current, and it's very important to describe current. We will need a direction. So this is the expression for current for the time period delta t. But then if I want the expression of current for the time period t, that is for the duration time t, then I can write it as follows. So for that we will be using the limit function, and this is a pretty familiar method whenever you are doing any sort of derivation in physics. So this will give us a differential term. So that's going to be I is equals to dq upon dt. So basically the electric current is the rate of transfer of charge from one side of the area to the other in the given time period t, and its unit is ampere. And so for 1 ampere current, there should be the 1 coulomb of charge passing within 1 second through any specific conductor. So now we will move towards the current density. So to understand current density, I am going to make a diagram, and we will use this specific diagram to reach to the final formula of current density. So let's make it. So basically this is one specific cross section of a conducting wire, and this would be the direction of current. Okay, so here this is the cross section of the specific conducting wire, and this is our reference point P. And now the current which is passing through this specific conductor is denoted as delta I is equals to delta Q divided by delta T. Now let's consider that delta S is the specific cross-sectional area, and for that we need to draw another diagram, and we will be drawing that. So basically this is the another diagram, and here we have drawn a normal which makes an angle theta, and this is how the current is flowing through the conductor, and this is just the specific cross-sectional diagram of any specific conductor. So if now this delta S stands for the chunk of the area that we are considering. So now basically here if we see, then we can consider this specific normal to make the which stands for delta S. So we are interested for this specific dimension, so that would be the component of delta S. So the specific component which is in this direction can be written as delta S cos theta. So I will be writing delta I, this specific formula can be, or else the current density is basically denoted by I is equals to I di upon ds. So that is basically the current passing through the specific cross-sectional area of a conductor, and J is the symbol for current density, and it is a vector quantity. We will need its magnitude as well as its direction to describe the overall quantity current density. So I will be writing this specific expression in which we have ds with respect to this understanding. So that would make it as J is equals to delta I divided by delta S cos theta. It's fine if we can replace this differential symbol with the delta, that would be fine. Okay, so that makes me to write J. I am writing this specific expression as J delta S cos theta is equal to delta I. So this would be the amount of the current moving through a specific conductor with its specific current density J, and delta S cos theta would be the area component of that specific part of the conductor. So now we can see that here there is cos theta which is the trigonometric function present here. So that would help us to write down this specific expression as J dot delta S. So whenever we have a cos theta in the expression, we can write it as a dot product. So that indicates that the current density and the area vector, they are the dot products of each other, and that will lead us to delta I, that is the current flowing through the conductor. So this is for the infinite area, like we don't know for how much range this specific expression is applicable, but then if we have a specific conductor limited to certain amount of area, like as in if we know the dimensions of that conductor and we want to know the current density, then we can use the following expression. which goes as so here this is the sign of the integral, and it means for the finite area, and we can put the integration limits here. And J stands for the current density, and ds stands for the area uh, that we are taking into consideration. So as we can see, since it is the dot product of two vectors, means the final product that we get is basically a scalar quantity. I mean, you cannot add the current vectors, like you cannot add them like you add vectors. Okay, so but though you can still see that current density is the vector quantity here. So yeah, that's it. So to recall, we can say that I'll just sum up our discussion here. So to recall, we can say that I is can also be expressed as delta q upon delta t, and at the same time, if we are using current density to express I, then you can also write I is equals to integral j dot ds, or else in other way you can also write as delta j is equals to delta I upon delta s. This is for the larger chunk when we are not dealing with the infinitesimal dimensions maybe. So yeah, that's it. So see you guys in the next video. Bye.